announce our today's speaker, Jianyu Li.
Yes, yes.
He is an awardee of the KIT International Excellence Fellowship. So this is why he gives a special lecture, which will also be recorded and then put on YouTube eventually.
Okay.
If we all agree. So let me briefly introduce Professor Li to you. He received his basic education up to the bachelor in China in Zhejiang.
Yep.
And I guess then he moved over to the US
Yes.
to join Harvard, where he received his PhD in mechanical engineering. He stayed there for some time and did a postdoc with David Mooney, so rather visible, well-known personnel, still at Harvard. And then in 2017, he accepted the offer to join McGill University in Canada, where he has been building up his group since then. So his interests are actually rather broad in an area which I think is of quite a bit of interest to us, at the intersection of materials, mechanics, and biomedical engineering. So he is associated in McGill also with the Department of Biomedical Engineering and Surgery. So he is really at the interface. He has a number of very nice publications. I'm not going to go through them in detail, as you might expect. He also has won a number of awards. Very nice. We also have had some discussions here at the Institute to build up on mechanical properties of thermal and polymer interfaces, and we are about to start with the first collaboration. So important for us is that, again, we proposed him for a KIT International Excellence Fellowship that was awarded, and now he's here.
Yes.
So with this, I will stop my short introduction and hand over to you. And I would like to tell us about engineering interfaces between biological tissues and hydrogels.
Great. Thank you. Thank you, Christopher, for the very kind introduction. And first of all, I'm super pleased to be here and presenting you our work on this kind of interface between tissues and hydrogels. And first of all, I'd like to acknowledge this great support for this KIT International Excellence Fellowships, so which can bring me here and allows me and also my family to enjoy the great weather, the great springs here in Germany. So everything goes so well, and I really appreciate this support. And beyond that, I also like to acknowledge my team at McGill, and also the collaborator I have around the world and the funding agency, which make the following presentation possible. And first of all, that is the big picture of today's talk, is how we can engineer the interface between the human body and the artificial material. And as you can see today, there are a variety of applications require the merging of these two kinds of material for the biomedical application, for the engineering applications. So the most notable example would be like Elon Musk created startup like Neuralink, tried to make a brain implant, right? Put inside the brain, and actually they are doing clinical trial with the human patient. And beyond that, right, there are a lot of material has been proposed or has been implanted into the body, including these implantable electrodes, or like on the skin, we have the wound dressing, the skin electrode. And for today's talk, I will be talk a lot about the bioadhesive technology. So essentially, it's engineered material. You put it on the tissue surface, enable the adhesion and the addition kind of biomedical purpose. So first of all, why we have to use hydrogel or bioadhesive in the first place? So that is because of those target applications are focused on biological tissues. So we all can appreciate it, biological tissue are very soft and very wet. So here is kind of a summary of the elastic modulus of different kinds of biological tissue. And as you can see, from lung, skin to cartilage, right? The elastic modulus or the stiffness are typically below 1 megapascal, And those values are significantly lower compared to like the plastic or metal. In addition to the softness, the biological tissue also feature a very high water content. There's another summary of different kind of like biological tissue that containing a large amount of the water, right? You have in the blood, you have 40% of water, and in those soft tissue, we have up to like 85% of water. And to working with those biological tissues, soft and wet, right? By intuition, you're expecting something to be soft and wet as well, in order to really mechanically and also biochemically compatible with the biological tissue. So in that regard, hydrogel is very appealing, right? Hydrogel is a class of material system which are very simple. Essentially, you have hydrophilic polymer and you put it in the water. You absorb those water because of the hydrophilicity and will swell into hydrogels. So the hydrogel are essentially jelly. You can find in the kitchen, and also has found a lot of significant application in our daily life, including like the diaper, right? Super absorbent diaper is a kind of hydrogel, and the baby clearly enjoy that. And also some of you may wear contact lenses are made of hydrogel, and then some clinical applications such as the wound care, they use a lot of hydrogel-based material. And a little bit about the history. So the hydrogel has been invented for a while, and the first publication reporting this hydrophilic gel actually is documented in Nature, 1960. So that is from a group in Austria, and from the very first day, you can see the researcher recognize the nice feature of hydrogel. They can enable the permanent contact with the living tissue, and it shares the structural similarity with the biological tissue. And because of the water content, because of the mechanical property, and as well as the biocompatibility naturally come from like the large amount of water in hydrogel that essentially share with your biological tissue and with your body. In addition to that, people can do a lot of amazing things. I see a lot of colleagues here also working on that to improve the bioactivity of the hydrogel. But beyond that, the hydrogel has some limitations. So the most notable limitation, at least for me as trained as a mechanical engineer, is the poor bioadhesion property. So that is not surprising. If you consider the hydrogel, again, those are aggregates of polymer and a large amount of water. The water molecule essentially serve as a solvent, and they do almost nothing, right, to enable the adhesion. So in addition, instead, they try to limiting the binding between the polymer network and the substrate, right? So that's why we have measured the adhesion of the conventional hydrogel, such as collagen, polyacrylamide, on the substrates like the skin or like the glass, and we can find that the adhesion energy, that is a quantity we use to quantify the adhesion performance, is very low. So you can see the quantity is on the order of 0.1 to 1 joule per meter square. And a little information about this property we use, adhesion energy. So that is the energy needed in order to peel the unit area of a material from a substrate. So that is essentially based on the energy principle, how much energy you need to peel it off. And as you can recognize here, for the order of magnitude, the adhesion energy of hydrogel essentially is the surface energy of the water. Right? After the peeling, you are creating new surface of the water. And that makes sense why the hydrogel suffer from the weak adhesion. However, a lot of biological interface, right, biointerface, can enable a very strong adhesion energy. So for example, the adhesion between the cartilage and the bone, or the adhesion between the intervertebral disc with the bone as well. So the energy to get this stuff off from the bone takes 1,000 joule per meter square. So as you can see here, those are multiple order of magnitude differences. And also compared to the blood clot or the surgical glue, I talk a lot, the adhesion of the hydrogel intrinsically is very low. And how we merge this gap is the main puzzle I try to solve today in my talk. And take a step back, why it matters, right? So bioadhesion is important for biointegration. So here is a slide just to highlight the importance of the adhesion between hydrogel and tissue because they are clinically significant. So they can critical for the surgical procedures such as organ transplantation, right? You need to integrating this kind of transplant with the human body, and in other surgical procedures such as anastomosis, you can have an injury or because of surgery have separation of the tissue. You need this kind of material can engage, can merge the tissue together, and it's an interesting thing to know or to appreciate about this anastomosis procedure. Actually, is a Nobel Prize winning technique. So by the axial carrier in France inventing this approach, actually they opened up a lot of possibility in terms of surgery. So beyond this surgical procedure, the importance of bioadhesion or biointegration is also important for the emerging biomedical applications, such as you have the implant put into the cartilage, you want to make sure they can have a full integration, and also when you're developing a new kind of biomedical devices, such as those lung-on-chip, you also need to work on the integration between like biological and or engineered material. And that is the motivation, and from that I would like to show you our recent work to engineer this hydrogel and tissue interface. So today's talk will be centered around three key topics. The first one is how to form a tough adhesion, tough bonding between the hydrogel and the tissue. The second, how we control that, and lastly, how we leverage this ability to enable some biomedical application. And here also listing some kind of relevant publication we have, and if you're interested, you can check it out, especially for the projectors issue, right? You may miss some of the reference later on the screen. Okay, so first, bioadhesion, or hydrogel-based bioadhesive. And the first report of hydrogel-based bioadhesive is dated back even earlier than the first report of hydrogel in 1940, published in Lancet. So that is a proposal of using the fibrin clot. Here is the coagulated blood plasma, essentially is a fibrin polymer gel, and use it as a surgical glue to, for some nerve repair application. So since then, they has opened up a lot of application and interest of this kind of hydrogel-based bioadhesive, because as you can see, when you're working on so fragile soft tissue compared to suturing, right? The bioadhesive is much easier to implement and will be much better for the healing outcome. So we have the bioadhesive in a different form, can be a glue, it can be a patch, and you can find those on the market and under significant clinical use. And however, despite this significant use, those hydrogel are not hydrogel-based bioadhesives so far are far from ideal. So here is a slide discuss or presenting you the limitation of these clinically used bioadhesives. So the example including this polyethylene glycol hydrogel-based bioadhesive or the fibrin clot-based bioadhesive. So if you're testing their mechanical property, you can realize this kind of gel are very brittle. So to tear this kind of gel, you only take like 10 joules per meter square of energy to do so. And also if you measure the adhesion of this surgical glue on biological tissue, you end up with a very low adhesion energy on the order of 10 joule again. And because of that, the vendor, the manufacturer already recognize this limitation, and they can clearly indicating, as you can see, this product, the dual sealant system and the hydrogel glue can only be used as adjuncts to the suture. It cannot be used alone because of the weak adhesion and the weak mechanical property. So how we can understand, how we can engineer a better bioadhesives. So before I show you our recipe, let's take a look at the overall mechanics of this tissue hydrogel adhesion. So here is a very high-level governing equation I will introduce about the contribution of the adhesion energy of any bioadhesives. So when you peel this bioadhesive from a tissue substrate, you need to do the following mechanical work. And first of all, you need to cleave the bonds at the interface, right, between the adhesive and the tissue. So that go to the energy represented gamma 0. In addition to that, you also need to do the mechanical work to mechanically damage like the adhesive and the tissue, which are inevitable when you peel this material off. So that's go to the energy gamma of the tissue substrate and also the energy dissipation in the adhesive matrix. So together, those are the adhesion energy of the adhesive. And let's visit one by one. For the first contribution, gamma 0, essentially you need to breaking the bond on the surface. So those are the existing toolbox, right? The chemists have very creative to create different kind of chemistry to form either kind of like carbon-nitrogen bond or variety of those chemical bonds on the tissue surface. However, when it comes to the energy it consumed, we use this pretty established Lake-Thomas model in the polymer physics. So to calculating what's the amount of energy it needs to break or to cleave this bonding polymer chain. So essentially, the energy you need to do to cleave those bonds proportion to the length of this kind of polymer chain in the between, because when you rupture one and there's experiment and also simulation results showing up, you need to dissipate all the strain energy storage in the whole chain instead of a single bond, and also proportional to the energy of those chemical bonds along those chains. But as you can appreciate here, those are subject to physical limitation. Because the number of the chain you can packing on the tissue surface is limited, right? The chain has a finite cross-section area, and the length of this polymer chain is limited, and also the energy yield of those chemical bonding, despite the chemistry to form it, are limited. Essentially, you can see most of them are carbon-carbon bond or carbon-nitrogen bond, right? So put them together, we use some representative number, and we calculated the limit for this gamma 0 is on the order of 10 joule per meter square. So that is kind of comparable to the adhesion performance actually you measure from the surgical glue. And then let's look at the second part, the tissue. In terms of the tissue, mechanics is rather complicated because different tissue has a different mechanical performance, and then it has a highly nonlinearity, as you can appreciate the difference between the skin and the liver. And that is the approach we take is using finite element simulation, and we can well account for those nonlinearity response of the different sort of tissue, and we throw them into our finite element framework, and then we can calculate the amount of energy dissipated in the adhesive and also in the substrate. So here is a summary of those results. We found that the significant amount of energy is only dissipated in the adhesive, and the tissue only do a little work. So what it indicates here, in terms of the second contribution, the tissue substrate is very small, right? And the last knot you can tune and actually goes to the adhesive matrix. So the adhesive matrix is something we can rationally design. For example, in this case, in the simulation, we can engineer or we can tune the model for this adhesive matrix, and when it make it to be tougher and easier to dissipate energy, in this case, you can appreciate it, the overall adhesion energy is got much higher, right, compared to the case you have kind of like a brittle matrix. So here we can achieve a significant overall adhesion enhancement by tuning up the contribution of the third terms, adhesive matrix. So that's point out the direction for our design, right? In terms of the gamma 0, the intrinsic bonding, we already can we can make the highest as we can get, and the tissue doesn't contribute a lot. And the last one, the adhesive matrix, has no physical kind of limitation, and therefore we can focus on that to achieve a tough bioadhesion. So our recipe to achieve tough bioadhesion essentially is focus on the third term. We need to use a very tough and dissipative matrix in pair with a very strong interfacial bonding, and we can get a tough adhesion. So that is the version 1 material system we demonstrated. We called it tough bioadhesive, we stick it onto the surface of the heart, and when you pull it, as you can appreciate it, the adhesion remains strong, and also the adhesive is very stretchy and tough. And that are technical detail, how we make it possible, right? First of all, we need to use a very tough and dissipative matrix. So our strategy here is to use a tough hydrogels. So those are significant research effort in the field to try to make the hydrogel to be very tough, very stretchy, and also, as you can see, the area underneath will be very large, indicating it dissipates a lot of energy. And this system is representing by this combination of the polyacrylamide and alginate hydrogel. As you can see here, this gel matrix is very tough and also very stretchy. Yeah, I think the bird is quite interesting. Okay. Yeah. Okay. Yeah. And then, secondly, right, to enable this interfacial bonding, so the polymer we utilize is called hydrogen, so which is a biopolymer polysaccharide derived from the shrimp shell. These days you can get it from the mushroom, and the characteristic of this polymer is it's carrying a lot of kind of priming amine group, and this group at the neutral pH will be positively charged. And when it got positively charged, it can enable like the attraction to the negatively charged surface of the tissue, and things is priming amine, very basic chemistry, carbon diamide, right? You can make the very strong kind of amide bond, essentially is a bond of the protein, right? Between this adhesive and also the tissue. So for example, the extracellular matrix, like the protein of the tissue. In addition to that, the nice feature of this polymer is it has ability to form a lot of hydrogen bonds. So that allows this polymer to self-cross-linking. So without adding UV light or heated it, just tune the pH of the neutral pH, it can form a bridging network at the interface, which will be maximize the interaction between the adhesive and the tissue substrate. So apologize for kind of a bit bloody video here, but just like want to show you the case of application. We apply this bioadhesive on a dynamic, wet, blood exposed hard surface, and we apply this compression and in like 2 minutes, and we can form a very strong adhesion in the location of compression. And the surgeon can try to peel this adhesive off. As you can see, as I promised, the matrix is very tough, stretchy, and the adhesion is very strong. And together, we achieve a very high adhesion energy. And all the chemistry we use, the hydrogel matrix and the carbon diamide chemistry are all water compatible. So our system is insensitive to the blood exposure. So you see, the blood exposed or not, it doesn't matter. In contrast, you may know that, right, the superglue, which often recognized as the strongest adhesive, when you apply that on the wet surface, and it doesn't work, because a little bit of the water moisture will trigger the rapid gelation of this cyanoacrylate and limiting its engagement with the tissue substrate. So that's why for that, it's not blood compatible. And quickly show you like more detail about the adhesion performance. Because we are leveraging a variety of interaction, right? Electrostatic, chemical bonding between the adhesive and the tissue. We can form adhesion pretty rapidly. Within 1 minute, we got 200 joule per meter square. And this chemistry are targeting quite universal, like protein of the biological tissue. So therefore, it's universally applicable for different kind of tissue, the skin, cartilage, heart. In my lab, currently we are focused on the intervertebral disc or the cartilage. They all achieve a very high adhesion energy, much higher compared to the clinically used fibrin glue. And here is a summary slide in terms of the performance. That is the focus of our mechanical design. We want to improve the adhesion energy, at the same time, the matrix toughness. And luckily, these two quantities, they have a good kind of like synergistic effect, enable each other. So in this case, you can see this kind of nice effect in our tough adhesive. And compared to the clinically used glue, we are much higher in both quantity, right? And as you may also think about, how about the adhesive band-aid? It's made of very tough elastomer, so it should have a very good matrix toughness. But as you can see here, because of the bonding of this elastomer, adhesive band-aid with the tissue is quite limited and very weak, only mainly based on the physical interaction. And the adhesion energy of the adhesive band-aid is much lower than our tough adhesive. Okay, so hopefully I can kind of convince you it now is possible and is feasible to achieve tough adhesion. But often the question people will ask me after my talk is, okay, now, but how you can get rid of it and how we can control, right, those bioadhesion. So that is the next topic I will show you, is about the control adhesive. And that is aligned with a big picture, at least we have as a material scientist. It's just like we want to achieve the intelligence, right? It's a material intelligence of this adhesive material in a different application. For example, in a surgical setting, the surgeon wants to control the adhesion, right? Super glue is gluing too fast, but somewhat, and also they also need a time window to position this adhesive property, right? And also in the case you want to get this adhesive off, if you misposition it, and they also need this kind of like ability to control that, the adhesion magnitude. And the other applications such as wound dressing I will show you later, and also some kind of like engineering fabrication procedures such as transfer printing, they all allow you allowed us to motivate it, this control adhesive, or kind of more fancy term adhesive intelligence. So we want to control adhesion in a temporal manner, in a spatial manner, and also in the magnitude. So along this direction, we have done some work, try to enable the control of the hydrogel tissue interface. We have proposed using the ultrasound, or using some kind of topology design of the polymer network, using the structure design, or using the temperature. And due to the time limit, I will mainly focus on the use of the ultrasound to control this bioadhesion. So why we think of ultrasound? So ultrasound actually is a very versatile and very powerful technique, and is used in different kind of clinical setting, right? As you can all appreciate it, ultrasound is the standard, right, of the imaging technique, right, to checking the baby inside the body. And they're also widely used in the case of the tumor or cancer treatment, right? By leveraging this distraction effect of ultrasound, you can use for the tumor ablation. Even like a lower ultrasound frequency that has been proposed using for the drug delivery, and then for the kind of acoustic range of the sound, it lacks this ability of the energy level or the ability of the ultrasound. So that's why it's a very powerful technique. And instead of using the ultrasound for imaging or the drug delivery, so what we propose here is just like we can use ultrasound to control the transport of this adhesive polymer through the tissue barrier. So this, we call it, is a very sound way to make the hydrogel sticky. And the beauty about this strategy is just like things in this case, the adhesive polymer can readily penetrate through the tissue barrier. We have no need to do significant chemical reactions with the tissue. And the benefit come with that would be reduce like side effect, or it's much higher controllability. I will show you in a few minutes. Okay, so before we show you the detailed result, here is the big picture of our kind of strategy. So essentially, as I said, we use the ultrasound to induce the cavitation inside the adhesive solution, which we use the hydrogen as a model system, and it can kind of increase the permeability of the tissue substrate. In this case, if you consider the skin, you have a very dense scrotum corneal layer, like epidermal, which is very difficult to get over for the typical polymer material. But with the help of the ultrasound, create microcavitation, we can propelling this adhesive polymer just like a nail to or staple to get through on the molecular level, and further apply this adhesive patch, we can form a strong adhesion between hydrogel and the tissue. So here is the quick result, show the effectiveness of this strategy. So we want to form adhesion between the hydrogel and the pig skin. Without the ultrasound, we got a very low level of adhesion energy. So that is the T-peeling test. You can see the adhesion energy for this case would be around like, around 2 times of this would be around like 30 or something for the case without ultrasound. Even though you use like a adhesive polymer in the between, but it cannot get over the skin barrier. With the help of ultrasound, we can dramatically enhance the adhesion like by around kind of 2 orders of magnitude. So over 1,000 joule per square. And this strategy is working not only on the skin, but as you can see, the big contrast on other tissues such as buccal mucosa or the aorta. And the strategy is also not limited to polymer. And we have shown that in the case of the nanoparticle, I'll talk more later, it also have this big contrast with the help of the ultrasound for the bioadhesion and as well as like protein-based polymer. So what's going on here? We try to study the mechanism in the behind. Here we have teamed up with the group in the ETH, and we end up with this proposal is the ultrasound was mainly doing cavitation, and when it cavitating the hydrogen solution, upon the collapsing of the bubble, it will create a microjetting, right? This microjetting will be shooting preferentially to the tissue substrate and enable like the stapling or anchoring of this hydrogen polymer into the tissue. And following this hypothesis, we are checking like the penetration of this fluorescent labeled hydrogen polymer. As you can see here, without ultrasound, it doesn't get into the skin, but with ultrasound, you can get a much deeper of penetration. And further, we're also checking the correlation between ultrasound intensity. So here is a micro bubble cloud under the ultrasonic probe, and we can play with the intensity, and we can further measure the adhesion performance. As you can see from these plots, both the adhesion energy and the strength are kind of like proportion, right, to the amount of the cloud intensity or the ultrasound intensity you apply. So kind of further support the correlation between the cavitation and the adhesion. So what's the benefit of that? The ultrasound is super localized effect. So the first proposal here, we can use the ultrasound to control where we want it to form adhesion. So before we study that, we kind of study the effect, localized effect of ultrasound. So we control the distance between this ultrasonic probe with the substrate, and then we are characterizing what's the area of the adhesion can form under the different distance. So since the effect of ultrasound is very sensitive to the gap, so therefore, as you can appreciate here, when the gap is too large, you don't get the effect, you don't get the benefit of ultrasound. But you need to get it close, you get the effect of ultrasound, and at the same time, we can also use a computational model to simulating the area of the tissue the solution got cavitated, and we can find the nice agreement between the predicted adhesion area with the area predicted from our simulation. So that just like enable us to really control the adhesion by using the ultrasound probe. So that's just a demonstration showing we form the adhesion only in this area, but with the application of ultrasound, it only forms adhesion in that specific area. And the other area, even though you expose with this adhesive solution, it doesn't form adhesion. And furthermore, you may know for the ultrasound, in addition to the cavitation, it has other effects, right? The most notable effect of ultrasound would be the heating. You can feel the heat. And in this case, we can further leveraging this additional benefit of ultrasound to enable like on-demand detachment. So the proposal is following. We have to use a thermosensitive polymer. So in this case, we can use the gelatin as a thermosensitive adhesive system. When you apply that, form that at the room temperature, it enables the strong adhesion. We achieve like more than 200 joule per meter square. But when you apply the ultrasound, as you see in this imaging, we can see localized, it has a heating effect of the ultrasound probe. In that case, it will be melting down this gelatin polymer at the interface, and we can effectively reduce, knock down the adhesion energy. So that is the nice thing about the ultrasound. And the last advantage about the ultrasound I want to show you here is the nanoparticle adhesion. Okay? So nanoparticle has received a lot of attention, right? It has amazing application has been enabled for a variety of area. However, when it comes to this hydrogel tissue interface, the nanoparticle has been known to only enable a weak adhesion. So why is that? So here is a paper published in Nature in 2014 that proposed the use of the nanoparticle to form adhesion. So the physical picture is following. When you place the nanoparticle in the interface, you absorb the polymer from both sides and enable the adhesion, mainly based on this kind of like van der Waals force or like physical interaction between the polymer and nanoparticle. But at the end of the day, you only can get a very weak adhesion energy. You see, is again very familiar number on the order of 10 joule per meter square. So they have screening different kind of polymer, different kind of nanoparticle, like the carbon nanotube or like silica-based nanoparticle. And those low adhesion energy come with reasons. The reason for that is this nanoparticle is only form a weak interaction with those polymer, right, inside the tissue or in the hydrogels, and also because of the larger size of this nanoparticle. It's very large, so much difficult for them to penetrate the condensed tissue barriers such as epidermal of the skin. So how we can overcome this issue and how we can make really a better nanoparticle glue is following. So our proposal here is, first of all, we need to overcome these two limitations. In terms of the tissue barrier effect, we really need to allow this nanoparticle to penetrate through the tissue. So in this case, we propose to use the ultrasound as a strategy to deploy the nanoparticle to get it through, or we can use other approach, like physical approach using microneedle, and we can kind of piercing the tissue and get this stuff over. Or we can use some chemical approach, like you can treat with some chemical to the skin and it can peel off or kind of loosen the skin matrix. So with all of that, we can achieve the tissue penetrations. And for the second issue, the weak interaction between nanoparticle on the polymer, we propose the use of this nano whiskers glue. And the nice feature about this kind of particle is it has a very high aspect ratio, as you see in this kind of schematic. So we show that in the case of the kerosene nano whiskers, the same kind of composition we use for the previous work, but in this case is a nanoparticle or nanocrystal form. This one has a very long size and very small cross section. Much more look like a nano needle. So for this nanoparticle, it also has abundant kind of like a functional group such as amine group and as well as the carboxylic groups, residues of their chemical processing treatment we have done originate from the chitin nanocrystal. So with this nanoparticle, it has high aspect ratio. It can really kind of procreated together and kind of assembly form this kind of very rigid condensed cluster on the interface between the hydrogel and the tissue. So with all of that, we first testing the adhesion performance. So that is the result. We combine our delivery approach and this kind of like a nano whiskers particle, and we can achieve a very high adhesion energy between the hydrogel and also the skin tissue. Like in this case, among the three testing methods, They're all effective, but again, the ultrasound stand out in terms of the overall adhesion energy performance. So what's going on here? Why, in this case, the nanoparticle, nanowhiskers can do the job? So here we have teamed up with the chemist, at McGill, we use the transmission electron microscope to really see a very thin sections of the skin hydrogel samples. So that is a quite challenging task to do in terms of doing the TM on the skin sample. So in this result, hopefully you can clearly see that instead of the classical picture of nanoparticle adhesion, you have a nanoparticle in the between binding the two matrices on both sides. Actually, what we find is different. We have this nanoparticle actually forming a layer in the between of the hydrogel and the tissue. So at the end of the day, what we found in the TEM is the nanowhiskers form a condensed network sandwich by the hydrogel and the skin. And this kind of network can not only penetrate into the hydrogel, but also with the help of the ultrasound or the microneedle, it can get penetrating deeper into the skin. So as I show here, we decker our nano whisker using gold nanoparticle, and we really can see this high peak of this nanoparticle in the between, penetrating both in the hydrogel and the skin. So in the case of no ultrasound or no delivery approach, if we use these nano whiskers alone, as you can see here, we get a very weak adhesion, and also we don't get the penetration of this material into the tissue. And then that kind of explain, okay, at least we see what's going on at the interface. And what's kind of the most excitement we have is the nice adhesion performance enabled by this kind of like nano whiskers layer. So this slide, I want to have your attention on this new test is called cyclic fatigue test. So what I showed you before, all those adhesion energy essentially is a one-time loading. You kind of peel it off, right? But in that case, you get a high level of adhesion energy. But in practice, you have this material may subject to like cyclic loading. So as you may know, for a lot of engineered material, right, it has a very high strength, but under cyclic loading, it can easily rupture, failure at a much lower loading, lower force. The reason for that is this material is suffer from the fatigue factor. So that is the case for this hydrogen polymer case. As you can see, we do this cyclic peeling test, and then we monitoring how the crack will be propagate under each cycle. You see in the case of the hydrogen, the crack will be slowly, gradually propagate through the interface. Although the loading we apply here is very low, it's much lower than the adhesion energy, than the strength of this material system. But in the case of the nano whiskers, we see this kind of a crack will be stopped and doesn't propagate up to like 10,000 cycles. So the reason for that we propose is that in the case of this polymer chain case, at the interface, the crack will have stress concentration, and then under cyclic loading, this stress concentration will be rupture, cleave the polymer chain in front of it. But in the case of the very rigid nanocrystal, nano whiskers, this crack will be pinged by this very rigid stuff. And since the gel matrix is softer, naturally you will be trying to kind of go over and kind of kink into the hydrogel matrix. So that is a mechanism to stop the interfacial crack propagation. To further validate this phenomena, or we call this fatigue resistance is real, we have tested this kind of crack propagation under different kind of loading, like from 67 to 800. And this result, we can calculating how fast the crack propagate under different loading. As you can see here, when you apply a larger load, you have some level of crack propagation. But when the loading is slightly lower, you see the crack are pinging, the crack are stopped, it doesn't propagate. And the value here we got is called fatigue threshold, is 382 joule per meter square. And we are very particularly impressed by this value because compared to what people have achieved in the literature, the threshold of the other polymeric-based adhesive is only around like 30 joule per meter square. So we get one order magnitude higher compared to what people have achieved in the field. So in addition to that, I'm sure a lot of experts here, we can also do a lot of things with this nanoparticle, right? We can functionalize it for different function. I just want to show you the advantage of this strategy is these nanoparticles are really located at the interface. We can really locate the functionalization to the interface at the hydrogel and tissue surface. So here is just like a proof of concept. We can use it by decorating with a gold nanoparticle for the photothermal effect, and that only localized at the interface, and we check the back of the tissue that doesn't got heating up. And then further we can combine with the titanium oxide nanoparticle, we can enable the production of the ROS. There are some therapeutic function. So that is the finishing the second part, and the last part I would like to show you the application. So we as a team, we are trying very hard to team up a lot of collaborators, and I'm very glad to also find more here and to explore different applications. So we have been exploring the application of bioadhesive for the skin, intervertebral disc, hemorrhage, different kind of application. And in my lab, we're also working on the stretchable electronics, and we also use this gel to enhance the performance of the existing surgical devices. We also recently do a 3D printing work by using this kind of like adhesive. And for the time limit, I quickly show you the two applications. One is skin wound application, another one is the bleeding control. So the wound care is a critical clinical problem, and that is relevant for the case of a skin injury, or it's particularly very challenging is the case of the diabetic ulcer, right? A lot of people suffer from those kind of skin injury, and the market is pretty large. And there are a lot of issues remaining for the skin wound care, and particularly one issue here would be the slow healing, especially in the case of diabetic ulcer, and also like the formation of the scar. So here we have looked into this application and got some inspiration from the biological phenomena. So in this case, it's called like embryonic wound contraction. So before our birth, if an embryo inside the mom, the skin has a very amazing healing ability. So what's going on here is that if you got a wound and the cell nearby can form an actin cable, it's just like a zip line can really kind of zip up the wound. So that is a very amazing function like active wound closure, right? So it's very fast and it's scar-free, and however, after birth, our adult skin loses this ability. So we mainly heal our wound because of regeneration. And how we can kind of like restore this superpower of our skin, our strategy here is to leverage this adhesive platform. So what we do here, things we can stick our hydrogel to the skin quite well, and we can further enable the contraction of this hydrogel. And through the contraction, it can actively promote the closure of the wound. And in order to do that, we will still do the trick with the adhesion, but most importantly, we need to add a new function like temperature sensitivity. I think it will be no surprise to you if you're working on the thermal responsive polymer, and we're using the polynipron polymer, so which can shrink at the body temperature by extruding the water out and transmitted the contraction to the skin. So we got the nice adhesion, and we also got this contraction function through this polymer design. And kind of quickly show you there are some mechanics inside here, because you want to make sure this contraction doesn't cause delamination, right? If adhesive contract and it get off, and that's useless. And what we do here, we do some mechanical modeling to see what's the adhesion we need in order to let adhesion sustain the contractions. So we just realized that we just need to get the adhesion over 10 joule per meter square, and then this stuff, adhesive, will remain stick to the skin, and then they can contract. without a delamination. So just like a quick result about the in vivo test, we're testing this using the mice Roder model, and then we quickly show that by have this active contraction function, we can accelerate the wound closure. On the day 3, we can close like nearly half of the wounds, but in the other control case, by using the tegaderm or using non-contracting adhesive, we have very small contractions. And this kind of speed is independent of biological process, and we believe it's because of this mechanical effect. And the last application, kind of quickly, is about the hemorrhage. So hemorrhage or heavy bleeding is another critical clinical challenging. Actually, that's some surprising fact for me is hemorrhage is the #1 cause of preventable death. It's not the cancer, not the other, right? Many other, they are difficult to prevent, but in the case of preventable death, the hemorrhage is the #1 to blame. And it's relevant for the battle and for other different kinds of surgical application. It's very important to stop the bleeding very quick. And in this project, we work with the Christian Kastrup from the UBC and now in the States. And what's the problem we try to tackle with our new design is particularly for the case of a non-compressible hemorrhage. In the hemorrhage case, you imagine you have a high pressure blood flow coming out. And in that case, the tissue surface will be covered with a lot of blood. So in that case, if you use a non-porous bioadhesive, and usually you can compress it. However, in the case of non-compressible hemorrhage, such as bleeding in your liver or in your vessel, like those internal organs, you cannot apply compression, right? Just indicating by the name. But how we can avoid, how we can remove those blood and form the adhesion is challenging for our previous generation 1 adhesive system. And what we propose here is let's engineer the structure of these adhesives, just make it somewhat like a sponge. A sponge has a lot of pores, as you can see from our SEM imaging, on the order of like 100 micrometer, and it can allow this adhesive to actively absorb the blood on the surface, and at the same time, we can infiltrate some liquid adhesive into the matrix, and it also can enable the releasing of the adhesive polymer to enable adhesion. You may worry, it's a sponge, right? How about the blood can get through? For the polymer we use design this matrix to have active clotting ability. The blood got absorbed in, and it can quickly clotting, kind of enable the sealing of the matrix. So that is a quick result to prove that our methodology work. It really can absorb the blood quickly, and it can form adhesion. And things, in this case, the blood can be removed by capillary effect. We don't apply compression. So in this case, we test in different system without compression. We get a reasonable adhesion performance. So efficacy has been tested in a Roder model. We're also testing in the pig, and we compare with the clinically used products such as Surgiform or the gauze, the simple one. We achieve much less blood loss, faster hemostasis, and most importantly, compared to this Surgiform, we achieve a much better biocompatibility by reducing the fibrosis level and also trigger much less immune response. And that's the last slide, kind of like hopefully you enjoy my talk and our work, kind of to show you the importance message as follows, right? Both the interface binding and the tough matrix are very important. And ultrasound is nice to engineer this interface between the hydrogel and the tissue, and then we can able to form this reliable functional interface, and that can be useful for different biomedical applications. So thank you. So that's all my story today.